Yeah, before
Uh,
you share your screen, I would like to briefly read your biography to
okay,
our audience, if that's okay.
sure, please.
All right, thank you. Today we have Dr. Ravi Kumar. He's going to be speaking on solar energy storage using latent heat, thermal heat energy storage for medium and high temperature applications. Dr. Ravi Kumar received his PhD from the India Institute of Technology, IIT, in 2012. During his time at IIT, he worked on investigation of energy efficient receiver for line focus concentrating solar power systems, such as parabolic Torr collector and linear Fresnel reflector for process heating and power generation application. He has also worked on solar field design, feasibility study of large-scale CSP plants, a multi-stage solar desalination system, and so on. After his PhD, he worked as a postdoctoral fellow at ABB Corporate Research Center, Bangalore, for a year. Then he joined as an associate scientist in the same organization on July 2013 and promoted as scientist in 2014. His research work at ABB Corporate Research Center includes solar-aided thermal power generation, solar heat for process, heating applications, and multi-physics modeling of secondary steel making process and measurement devices. Since November 2016, he has been part of the Department of Energy Science and Engineering in the India Institute of Technology, Delhi, as an assistant professor. Dr. Kumar, absolute pleasure to have you here today. Please, you can go ahead and share your screen. Thank you.
Thank you so much for the nice introduction. Could you please allow me to share my screen? Right now,
Yes.
it says that.
Yes.
Okay. Yeah. I hope you could able to see my screen. Is my screen is visible?
Absolutely.
Okay. Yeah, great. Thank you for the nice introduction. Myself, Ravi Kumar from Indian Institute of Technology, Delhi. So next 10-15 minutes, I'll be talking about latent heat energy storage system for medium and high temperature solar energy application. The energy storage system is important if you would like to if you would like to bring down the mismatch between the demand and supply. The energy storage system plays an important role, primarily for variable renewable electricity. Particularly coming to solar energy is intermittent in nature and intermittent diurnal in nature, and it keep varies the intensity of the solar radiation. And if you would like to use solar energy for various applications, starting from power generation, industrial process heating, and other application. So supplying energy at the required rate depends on the application is very much important. So in this presentation, I'll be discussing about first why the energy storage is important. Then I'll be talking about how these energy storage technologies can be classified. Primarily, it can be classified mechanical energy storage, and then thermal energy storage, and then electrical energy storage. And then we'll be focusing on thermal energy storage. And thermal energy storage, let's discuss about how this thermal energy storage technology can be classified. Primarily, classified into sensible heat energy storage technologies, latent heat, and thermochemical energy storage technologies. So then further we'll go into the latent heat energy storage technology, how it works, and we'll see what are the challenges associated with latent heat energy storage technologies. Then let's see what are the opportunities to improve its performance of the storage system. So a couple of them I'll be discussing here. One is how we could able to use the fins to improve the performance of the latent heat storage technology. Then we'll discuss about how we could also use cascade latent heat storage technology in order to in order to maintain the uniformity in the energy storage during charging and discharging process. Then also we have performed some experimental investigation on the latent heat storage system, primarily on the solar salt. Then we'll discuss about the experimental test facility at the end, and I'll summarize the discussion. Moving forward, look at there are two curves on here. One is the supply, and another one is the demand. The supply, if you look at primarily from the solar energy, in the noon time, we'll have a relatively high supply as compared to the demand. So when the penetration of solar energy technologies, not only solar PV technologies, so solar thermal as well as solar PV, if it penetrates more, and the noon time it supplies more amount of energy, whereas the peak demand arises in the late in the evening hours or in the early morning hours. So in order to bring down the gap between the supply and demand, So, and thermal energy storage or energy storage system plays a major role. So, also not only this, it plays a major role in order to bring down the mismatch between the supply and demand. Also, energy storage technology, it reduces the peak demand and it reduces the CO2 emission, and then it reduces the cost while increasing the overall efficiency of the system. Thermal energy storage system can utilize the surplus energy from the solar thermal energy, means that whatever you have excess energy that can be stored in the storage system and that can be utilized in the later time. Thermal energy storage system improves the dispatchability of the system. And coming to the classification, in general, energy storage technology can be classified into mechanical and then thermal energy storage technology and then electrical energy storage technologies. Coming to thermal energy storage technologies, it's broadly classified into based on the way in which the energy is stored. It can be classified into sensible heat storage, latent heat storage, and thermochemical energy storage. So the sensible heat storage works, I mean that stores energy or releases the energy by increasing or decreasing its temperature of the storage media. Whereas in the latent heat storage system, it stores or releases the energy in the form of enthalpy of phase transition. Whereas in the thermochemical energy storage system, it stores or releases the energy in the form of endothermic or exothermic reversible chemical reactions. The energy density of the sensible heat storage system is around 50 kilowatt hour per meter cube. Whereas when you're going for latent heat, the energy storage is relatively increase in terms of both volumetric as well as the gravimetric, and thermochemical for that sky. Whereas storage period, so since the both sensible heat storage and latent heat storage, so it operates relatively at higher temperature or lower temperature from the ambient. So there is a heat losses associated with that. So that because of that, the storage period is limited. Whereas in thermochemical energy storage system, sometimes some of the chemical reaction happens relatively at ambient temperature. So since the end product, it happens at ambient temperature, it can be stored at a longer time without any heat loss. Comparing the storage costs, the sensible heat storage is relatively inexpensive as compared to latent heat as well as thermochemical energy storage system. So even if you look at thermochemical energy storage system, latent heat energy storage system, even it is relatively inexpensive as compared to thermochemical energy storage as compared to sensible storage system. Whereas coming to the merits, so the sensible heat storage is relatively mature and it's even available for large scale application for power generation. So most of the solar thermal power plants, concentrating solar thermal power plants across the world, they deployed sensible heat-based thermal energy storage system. And it's relatively simple in operation and it has high thermal conductivity. Whereas coming to the latent heat energy storage system, it has relatively higher energy density as compared to sensible heat storage media. And it happens both charging as well as discharging process at isothermal process. And again, this also relatively simple in operation. Whereas in the thermochemical energy storage system, it's relatively higher energy densities, and then the reactant or the end product can be stored at ambient temperature. Coming to demerits, as compared to latent heat as well as thermochemical energy storage system, sensible is the relatively low energy density, and then because of that, the construction cost relatively goes high. Whereas the latent heat storage system, most of the latent heat storage materials at low temperature or medium temperature application suffers with low thermal conductivity. So this can be improved by various R&D activities. And for low and medium temperature applications, some of the technologies are commercialized, whereas for high temperature, still the technology is in pilot scale. Whereas coming to the thermochemical energy storage system, this is a complex process and relatively very expensive. And most of the technologies in R&D level, still we have to make this technology to be taken to the commercial level. Let's see how the latent heat energy storage technology works. So if you look at the latent heat storage technology, it starts from the sensible heating. In sensible heating, it stores some amount of sensible heat in the storage media. And then further, the phase change happens in that this enthalpy of the storage media increases. So mean that the enthalpy of the storage media, mole fraction and the latent heat of the storage media, it will add into the system storage media. And then further, the sensible heating of the liquid happens. This is during charging process. And then during the discharging process, the first sensible cooling happens, and then the phase change happens from the liquid to solid, and again further the sensible cooling of the solid happens. So the total overall, the amount of energy stored in the latent storage media is the sensible heating of the solid plus sensible heating of the liquid plus the phase change from the liquid to the solid to liquid. So how these phase change materials can be classified? In general, we broadly classified based on the type of from which phase to which phase changing phase. You can classify as solid to solid. There are some the polyethylene glycol, it changes from solid phase to one crystalline structure to another crystalline structure. And then also we can classify solid to liquid and then liquid to gas. Among these three configurations, solid to liquid has relatively higher enthalpy of phase transition. So further, this can be classified into organic PCM, phase change material, inorganic phase change material, and erratic phase change materials. This organic PCM can be further classified into paraffin compounds and non-paraffin compounds. The example for non-paraffin compounds are fatty acids, esters, alcohols, and polyethylene glycol. Whereas in inorganic PCMs, the example for salts, salt hydrates, metal and metal alloys, and hydroxides. Whereas coming to erratic PCM, we can say example is organic, inorganic, and then as well as we can say organic and inorganic. So what are the challenges associated with the latent heat storage system? So as I mentioned earlier, so the latent heat storage system suffer with low thermal conductivity. So this is one of the major drawbacks. So this can be improved by adding the fins or heat pipes or some of the other materials. We could able to add nanomaterials or nanoparticles or metal matrices. We could able to improve the effective thermal conductivity storage media. And also, if you look at the improving the process uniformity by using cascaded PCM, mean that when the temperature enters, the heat transfer fluid enters into the storage media during the charging or discharging cycle, initially the temperature difference between the storage media and the heat transfer fluid is relatively higher. When it moves along the storage media, so over the period of time, when they're along the length, the temperature difference comes down. Mean that there will be a non-uniformity in the melting or solidification process. So this can be avoided by introducing multiple PCM or cascaded PCM in a same storage. As well, also, the inorganic salt usually based on nitrate and nitrate salts are explored for medium and high temperature application. But however, it has no suffer with thermal stability beyond 600 degrees centigrade. Well, another issue in the phase change is corrosion issue is one of the major issues in inorganic salts that needs more attention, that means more R&D. And then metallic PCMs having higher thermal conductivity and thermal stability incur weight penalties, and then also it is relatively expensive. And some of them, the performance improvement technique we'll see in the coming slides. The first one is, so we have explored how we could able to improve the performance or the heat transfer between the storage media and the heat transfer can be enhanced. So in this exercise, what we have done is we have considered that the charging has been done using constant heat flux, or mean that the electricity comes from variable renewable electricity source, and then this electricity heat source is given as the input to the storage media as a resistance heating, and then the charging happens. So look at the storage latent storage system. It has a cell, it's kind of cell and tube heat exchanger configuration. It has a, in the cell side, there's a storage media, latent storage media, and then the tube side, there's a heat transfer fluid flows to exchange or to extract the heat from the storage media during the discharge cycle. So here we have considered there are 4 heat transfer tubes and there's a cell, and then we apply the heat flux boundary condition on the outside of the surface. And then since it's symmetric with respect to this one, so here we have started performing 2 dimensions. We started with 2 dimension analysis, and then we further gone forward to the 3 dimension analysis. And then these are the configuration we have explored. So we explored the configuration 1, we have considered the rectangular fin, and then the configuration 2, we have considered the triangular fin, and the configuration 3, we have considered the T-shaped fin. So here it shows the case 1 minus and 1 plus indicates that as compared to the reference case, the length of the fin is reduced, that indicates the minus, whereas the plus indicates the length of the fin is increased. Similarly, the same descriptions given in the other schematic as well. So by performing the simulation in the ANSYS Fluent, so we could able to observe that this charging, we have plotted charging time for the various configuration. So as compared to the base case, there is no fins. And then if you compare with the other case, the case 1 plus mean that when you have the rectangular fin with 3.18 meter radial height, so it performs relatively melt at faster rate. So almost we could able to save 200 seconds. We could able to melt at faster rate as compared to the base configuration. So mean that it melts almost 7.4% time faster as compared to the base configuration. So this slide gives how the melt fraction or the liquid fraction gives. So the left symmetry, the left vertical symmetry gives the liquid fraction, mean that this one gives the liquid fraction, whereas the other side of the right side, the half, it gives the temperature contour. And if you look at these are for the various configuration, I mean the base configuration, rectangular fin, triangular fin, and then the T-shaped fin. If you look at so the melting happens uniformly, whereas the happens at the top relative to higher rate as compared to the bottom. The reason being is when the melt, so for the storage media started melting, the liquid portion starts moving due to the low density, starting moving to the top portion of the storage media, the cell side, and then there is a natural circulation current happens here. And then moving to the next one, the process non-uniformity. If you look at in typical latent storage media, in case we have only one storage media, during the charging or during the discharging, what may happen when you're circulating the hot heat transfer fluid to the storage media, the temperature difference between the storage media and the PCM at the inlet will be relatively higher. Whereas when it flows along to the length, what happened? The temperature difference decreases. So that gives non-uniformity in the melting across the whole storage media. Similarly, during the discharge process, when you're supplying the cold fluid to the bottom of the storage media, the temperature difference between the storage media and the and the heat transfer fluid is relatively higher. When it moves along the top portion, again the same issues happens. So this can be avoided by providing the multiple PCMs in the order of decreasing their melting temperature, where having the PCM1 having the higher temperature and then PCM2 having lower temperature, further PCM3 having further lower melting temperature. By doing so, we could able to maintain more or less uniform temperature difference between the storage media and the heat transfer fluid. And then, so this is some example we have solved. So we consider the three storage media, the nitrate salts we consider. One is sodium nitrate, and then potassium nitrate, and sodium nitrate. So the three configuration we have considered. The one configuration is we consider only single PCM, meaning that it can be either sodium nitrate or potassium nitrate or sodium nitrate. And it's kind of a double pipe heat exchanger, cell and tube double pipe heat exchanger, where the storage media is filled in the annulus in the cell side, where the heat transfer fluid is flowing through the red pipe. Here we have a 2 PCM. The whole domain is split into 2 equal domain, and then we have seen how the melting and solidification behavior happens. Similarly, we have the 3 PCM in decreasing order, equally divided, and then we have seen how the solidification melting happens. So these are the thermophysical properties of the storage media. We consider sodium nitrate, potassium nitrate, and then sodium nitrate. These are the various thermophysical properties. Initially, the entire system is assumed to be at during the charging process 550 Kelvin, whereas during the discharging cycle it's 640 Kelvin. So the initial analysis, the heat transfer fluid is passing through at 640 Kelvin at 4 meter per second velocity. So these are the outcome of the results. If you look at among various configuration, whereas single PCM and then multiple PCM. So this particular configuration so offers the best configuration, whereas the sodium nitrate, it offers relatively better liquid fraction as the single PCM, whereas in the combination of other PCM, sodium nitrate and sodium nitrate, the 2 PCM cascaded storage configuration offers better configuration due to their melting, the phase change enthalpy as well as the melting temperature. And if you look at the total charging time versus for the various configuration, so sodium nitrate and then sodiam nitrate offers lesser melting temperature as compared to the rest of the other configuration. The two-stage NaNO3 and the NO2 configuration offers 40.9% less time as compared to single-stage NO3 storage configuration. So further, we have done the similar exercise in the, we have developed a experimental test facility. We have developed a tube-in-tube cell and tube heat exchanger based latent storage media, where solar salt is used as a storage media. So these are the tube-in-tube heat exchanger, where the cell side we have a solar salt, and then inside the tube, we separate the heat transfer fluid. So here the charging is happened through the resistance heating, where the nichrome wires are surrounded around the circumference of the heat exchanger. So the charging is happened through the resistance heating, where we have we could able to control the heating rate, and then discharging process happens. The cold fluid circulate through the heat transfer through pipe, and then it extract the heat from the storage media. The same thing. So here we have measured the temperature at various locations along the radial direction and as well as along the length. So in order to measure the liquid fraction as well as the average temperature of the storage media. And then here this results is compared with our own numerical results, And here the experiments are performed for different heat flux boundary conditions, 1000 watt per meter squared, 1500 watt per meter squared, and then 2000 watt per meter squared. And similarly, the numericals also performed. And then almost this numerical and experimental behavior performs similar way, means that there's a difference of around 8.6%. Similarly, the discharging also happens by circulating the heat transfer fluid through the inner tube at 2 liters per minute as well as 5 liters per minute. And here also the numerical model matches very well with the experimental data. So coming to the summary, so the disabled characteristics of the energy storage media are it should have the higher energy storage densities and then faster charging and discharging characteristics and lower heat losses or the disabled characteristics of the thermal energy storage media. So one of the drawback in the latent storage media is primarily in the low temperature and medium temperature application is the low thermal conductivity, and this can be addressed by doing there are many techniques to enhance its performance. It is observed that the fins has in a radial direction has positive correlation with the reduction in the melting time. By adding the rectangular fins, we could be able to observe it increases the melting rate around 7.4% as compared to the base case. Similarly, we also perform the cascaded energy storage to see the uniformity, where when we have the NaNO3 and NO2 cascaded approach, it able to absorb around 35.2% and 10.5% less charging time as compared to the single stage thermal energy storage. And also we have performed the experimental test facility based on the solar salt. I mean that it's about 60% sodium nitrate and then 40% potassium nitrate. So we have performed the detailed experiments, and then also we have compared with our own numerical data. So it could match us almost very well. So with this, I'll stop. And if you have any questions, I'm happy to answer it.
Yeah, thank you very much, Dr. Kumar, for that wonderful presentation. The question I have for you is, you've talked about this technology, but are there any challenges in integrating some of the storage system into existing solar power systems?
Yeah. So right now, the latent storage technologies are integrated with the low and medium temperature application. Primarily, if you would like to integrate with the existing for high temperature application, the solar thermal power plant. So right now, we do not have very mature technology for operating 400 plus degrees centigrade. That is one of the challenges. Most of the technologies in R&D level. The second thing is when you want to integrate with the existing technologies, one of the issue will be the optimization, controls and optimization. Because the existing plant have on its own the performance behavior, and then when you want to integrate with the new latent heat energy storage system, how the system behavior, how the system gives the temperature, and then identification of suitable material, the performance controls and optimization one of the major challenges. And also, what purpose we are integrating with the solar thermal technologies? In case if you are integrating this latent heat storage technology for extended hour storage, then we should have additional solar field to collect additional energy. And then, so if you are integrating with only to capture the surplus energy, then only we have to see how the new system can be integrated with the existing technologies. Otherwise, it could be able to done. It can be done very easily, but there are some challenges in terms of the controls and optimization, as well as the performance of the both solar field as well as the energy storage aspect.
Now we're going to thank you so much, Dr. Kuman, for that wonderful presentation.